All right, how's everything going?
Good.
How'd high-low work out?
Think good.
Think good?
Think.
62 people turned it in, so that's awesome. That's almost everybody. All right, how about the ODP? So that ODP was trying to take the first character of a string and move it to the end of the string, right? And we went through some examples yesterday. So again, I got lots of emails from people saying, I wrote my program, it works fine for me, but I'm getting 0 out of 10. Okay? If you're getting 0 out of 10, there's a problem with your program. Okay? If you run it on a test case and it works, that's awesome. If you compile it and it compiles without errors, that's awesome. Doesn't mean it's correct. Okay? And if you're getting 0 out of 10, it's telling you there's something wrong with your program. So one of the hardest things in programming is figuring out how to debug code. But before you can debug, you have to actually know that there is a bug. And it's very common, right? We saw an example of this in the October Windows update, right? It's very common to think that your code is correct and push it out there, and when lots of people start using it, you find out it's not correct. Okay, so how do we figure out last Microsoft update had tons of errors in it apparently, and October's gone, they still haven't released it. Well, yeah. And that's, I mean, Windows is this huge thing, right? So take the difficulty in finding a bug in something like this and expand that to like millions of lines of code that goes back 20 or 30 years, right? It's horrendous. So it's not an exact science, right? You can stare at your code and maybe, you know, by meditating, you can defocus your eyes and bugs will jump out at you, but it doesn't usually work like that, right? So our best bet is usually lots of test cases, okay? So if you're processing strings, always try empty strings, because those are big edge cases, right? But in this case, if we're trying to move the first character to the end of a string and your string only has one character, that's probably an edge case also. Because we may be doing something like, you know, trying to process everything except the first character, shifting everything down one spot and then do something different. So that everything except the first character would be an empty string in that case. And that's another edge case. And you know, I would actually try it with an empty string, strings of 1 character, 2 characters, 3 characters. If it works for 3 characters, it'll probably work in general, assuming it works. This is all assuming it works for like hello, right? Which is the test case up here. But try it for like, you know, lengths of 0, 1, 2, and 3, and try it in different orders, right? In all terminators, you should be starting to get the feeling that sometimes you may not put an all terminator in the right spot, but your code might work anyway, right? So run this with a long string and then run it with a really short string and see if it catches a problem with that. And you can write a main program that calls move 100 times with, you know, different strings in different orders and just go crazy with like copy and paste in VI. Make yourself a huge test file, right? And use that to exercise your move function. And as long as you're putting in some of those weird cases, right, and you're doing them in different orders, you've probably got a pretty good handle on what's going on. I don't know what I actually tested this on. So that was what I tested it on. So something with no spaces, something with a few spaces, a couple of empty lines, something with 1 character with some spaces before, I think some of these things probably have trailing spaces, a longer line, stuff like that. Yeah. So that's part of the challenge. But my sense is that people are moving in the direction of being more successful at coming up with test cases, which is part of the goal. So that's awesome. So this was my version of the ODP. Different ways to do this, but this was basically a left shift, right? Go to this string and move every character down one position. From in to out. So I do that all the way through string length, and since I'm moving from I plus 1, that's inadvertently moving the null terminator into the output string also, which doesn't do any harm. But then when I'm done, I actually set character I to be the null terminator, right? I is where the for loop exits, plus 1. And then if your string is not empty, I take the first character in the input array and I save that into the last character position before the null terminator. That does not work if your string is empty, right? If your string is empty, your string length minus 1 is negative, right? So output bracket string length is where you put the null terminator. The character before would technically be index minus 1, and that is possibly going to seg fault. So that's just a check to make sure that doesn't happen. All right, so let's talk about PA4. So PA4 is all about string processing. Okay, it's about putting together characters to make string arrays, throwing on null terminators, searching for conditions in input strings, and so on. So all the stuff from this week's ODPs. So here's the idea of PA4. Here's an input file. It has some text. This is a test. Hello there, I am Nick a few times, repeating myself, haha. Repeating myself, haha, and I am Nick. So PA4 reads from standard in, right, or I can read from a file by redirecting. And it basically collects phrases from the input, counts how many times each phrase occurs, and then prints out an index of phrases sorted by length. So the word and appeared once, the phrase I am Nick appeared 4 times, the phrase repeating myself appeared twice, and so on. Okay, that's what your program is going to do. And as usual, there's a lot of details here. Okay, the details are largely intended to make your life easier. So if you ignore them, you lose points and you do more work, right? It's a lose-lose. So it's worth trying to understand the details here. All right, so you're going to read lines of text from standard in, break them into phrases, and we're going to talk about what phrases are, store them in an array, record how many times each phrase occurs, and then at the end of the input, sort the array by length and print out your sorted phrases with how many times each one occurred. All right, so simplifying details. Detail 1, convert everything to uppercase. Okay, lowercase hello, uppercase hello are the same word. Okay, and you can convert to uppercase using this function called toUpper. So if you include C type, you get this function called toUpper. You pass it an integer character like something you get from getChar, and it gives you back an integer character that's uppercased. And if you pass it a digit or a punctuation mark or something, it just gives you back the same thing that you fed in. So it doesn't do any harm. But if you feed in a lowercase letter, it'll give you an uppercase letter. So don't write code that compares ASCII codes to lowercase a, lowercase z. Don't add 32 to ASCII codes, things like that. Just use 2-upper. Okay? And that takes care of your first detail. Convert everything to uppercase. As soon as you read a character in, bang, switch it to uppercase. Run it through 2-upper. Okay, next detail. Any kind of white space, new lines, tabs, spaces, vertical tabs, get converted into plain old spaces. Okay? And this is important because when we're processing our phrases, if we have this is a test, we'd like to see the phrase this is a test. If this gets split up over 2 lines, this is a test. What does this actually look like when you read it in? It looks like this space is new line, a space, test, period. If you detect that new line is a space and you convert that to just a plain old space, this phrase looks exactly like that phrase. So now if things are broken up from one line to another like they are in books, you're not going to start coming up with crazy phrases.
So there should be 2 spaces then?
No, there's only one new line here, so that'll turn into a space. Okay, and don't write a big if statement that says if this is a tab or a vertical tab or a form feed or anything else, right? Use the isSpace function. So isSpace also comes from C type. And you pass it a character which is an integer, and if it's a space it'll return true, otherwise it'll return false. So isSpace right down here. Right, and it picks up all these characters, tab, form feeds, new lines, and carriage returns, and vertical tabs. All right, so now you're doing 2 things. You get a character, run it through 2-upper, and run it through isSpace, and if it's a space, replace it with a space. Just single quote, space, single quote. Okay, third thing, ignore any of these 6 characters. Parentheses, 5 characters. Parentheses, single quote, double quote, tab. Ignore them, they don't exist. If you read one from input, pretend you didn't read it, just read another character. If you read another one of these, ignore it, read another character. Okay? These should never appear in your phrases. They should never affect how you process phrases. They don't mark the beginning or the end of phrases. They don't exist. Okay? So those 5 characters, not part of your input. All right, so here's the tricky part, is what is a phrase? And this is more confusing than it needs to be, okay? Let me show you what a phrase is. Okay, this is a test period. This is a phrase, this is a test. Bunch of spaces, hello, comma. This is a phrase, hello. Space, how are you, question mark. This is a phrase, how are you. So we're ignoring these spaces in between things. Okay. But we're paying attention to spaces inside the phrase. And these punctuations are not part of the phrase, but they mark the end of a phrase. And once we have a punctuation, right, we ignore anything else after that until we get to a phrase. So if we have a bunch of dots in here, right, we don't have these little empty phrases in between the dot and the dot. Right? We wait till we get to something that looks like the beginning of a phrase, and then we pay attention to everything until we get to an end of phrase mark. So here's how we can put that in an algorithm. 3 steps. First, look for anything that's not a space and not one of these special characters. Okay. So start reading input, and if it's a space or if it's one of these, ignore it. Just keep reading until you get to something that's not a space, not one of these. May not be a letter, could be a number, could be a different punctuation mark, could be a number sign, a dollar sign, right? But read until you find something that's not a space and not one of these 6 characters. Okay, that's the beginning of your phrase. Now keep reading until you get to one of these 6 characters. Characters, numbers, spaces, anything. Keep reading. That's all part of your phrase. So copy it into some sort of temporary array, right? And then when you get to one of these 6 characters, you hit the end of the phrase. Null terminate your array. That array has your phrase. And the next time you go back to reading, you're back at step 1. So you're skipping over spaces and those 6 punctuation marks. Does that make sense? Now, this is not a perfect way to break things into phrases, okay? But it makes normal text come out mostly reasonably broken into phrases. It's not perfect. You'll find some cases where it does weird things. Don't worry about it. Let it do weird things. But by and large, if you just feed some text in, it will break it up the way that you would hope. All right, so we break this into phrases. We want to count how many times each phrase occurs, so we're going to keep track of that. And at the end of the input, we're going to print out a list of phrases and how many times each phrase occurred. And we'll talk about that presently. But is this okay for now? We're going to put together some pseudocode that will help clarify this.
If you're only looking for those symbols for the end of the phrase,
Mhm.
what happens if you hit Control-D before it finds one of those?
Well, that's a good question. So in your code, that's so if you, yeah, you can just say it's not a phrase.
Okay.
I'm going to test it. When I test it, I'm always going to have something at the end of my last sentence. Okay, so some examples of pseudocode for this. So 3 steps that we repeat over and over and over. Step 1, read from standard in until you find the beginning of a phrase. Something that's not a space, not one of those 6 punctuations. Then keep reading from standard in until you find the end of a phrase, and as you read, store each character in a temporary array. And then when we find the end of the phrase, see if this is a new phrase or one you've seen before. Sorry?
Why the reads have asterisks?
Because there's a comment I'm going to make about reads. So if you've seen this phrase before, then just bump up the number of times you've seen it. If you've never seen this phrase before, add it to your growing index of phrases and say, I've seen this once. Okay, repeat that until you get to the end of the file, then sort the index of phrases by length and print out that sorted list along with the number of times each phrase occurs. Okay, so here's the asterisk on read. If you use getChar, you have to do all of these things. You have to ignore certain characters, convert white space, convert things to uppercase. So my suggestion is don't use getChar. Make your own version of getChar. Okay, you can call it my super duper magnificent getChar. And what that function does is it reads a character from standard in, but it's guaranteed it will never give you one of those characters you're trying to ignore. It will never give you any white space except for a single space, and it will never give you a lowercase letter. Okay, it's your own customized version of getChar that does those first 3 details, right? These 3 things up here. And you bundle all of that into my super duper fantastic getChar, and now you don't have to worry about those first 3 details. Anytime you want a character, just call your getChar function, and you know it's going to be an uppercase letter if it's a letter. If it's a tab or a new line, it's going to be a single space, and it's not going to be one of these forbidden characters. Okay, so this is the start of modularizing your code. And my super duper fantastic getChar is going to call getChar, okay? But that's the only place that you need to use the actual getChar function. And you're putting your own wrapper around it that basically takes a single character and then conditions it. So what does my super duper fantastic getChar do? Call getChar. If it's a white space, return a space. If it's a lowercase letter, if it's a lowercase thing, right, just convert it to 2 upper, right, regardless. If it's not one of these ignore characters, just return whatever you read and converted. Otherwise, go back up and call get car again. And if it's a space, convert to a space, run it through two upper. If it's not one of these ignores, return it. Otherwise, go back, call get car again, right? It's a really, really simple function to write, but it's really useful because then you can completely forget about those three details as long as you call your version of get car. And that's a function that you can write, you know, right now and test the heck out of. Right? You can type in all kinds of input, and if you just keep calling your get car and printing out character by character what it returns, it should show you exactly what you're hoping for, taking in those first three details. So you type in a bunch of parentheses followed by ABC, and it should just give you an uppercase ABC. Right? So that's modularizing, and that's the whole name of the game for this assignment. You can write this as a single 1,000-line program, and it's going to be really, really painful. Okay? You can write this as a bunch of 20 or 30-line functions. It's going to make a lot more sense. And it's really essential practice, because that's what we do in programming. We reuse code. We try to break things down into pieces, and we break those pieces into smaller pieces. Or we take small pieces and we put them together to build bigger pieces, right? So we go top down or bottom up. And that's the life of programming, right? So these are essential skills. All right, so your read star function is your own version of get car. Does those three things. All right, simplifying assumptions. Again, these will make your life much easier. Assumption 1, each phrase is 200 or fewer characters. By the way, when I say character here, I don't mean a letter. I mean any character that we're not ignoring, right, or converting. So a digit is a character, asterisk is a character, ABC are characters. So each phrase is 200 or fewer characters. If you're reading in a phrase and it's more than 200 characters, just pay attention to the first 200. Just ignore the rest of it. Okay, and you can assume there's a maximum of 1,000 phrases in your input, 1,000 distinct phrases. Now a phrase might occur 1,000,000 times, and I might have a test file where that happens, but 1,000 distinct phrases. Now if you're reading your input and you find 1,000 first phrase, right, just ignore that phrase, but keep processing the input. And if the next phrase is one you've seen before, go ahead and bump up the count of that. And then you encounter another phrase that you haven't seen, but you've already got 1,000 phrases, ignore that phrase, keep going. Okay, don't quit early. So with these two assumptions, you can make your index look like this. Right, it can be a statically defined array, 1,000 by 201. And it's 201 because 200 characters, you're going to need one more spot for the null terminator. Right? And anytime you're dealing with a phrase, you can just treat that as an array of 201 characters. If it's shorter, that's perfectly fine. But since your phrase will always have no more than 200 characters, 201 elements in your character array is enough to hold it, because we have null terminators. And so our index looks basically like this. So we can index these accordingly.
What's that over the 1,000?
Sorry?
What's that over the 1,000?
Over the 1,000?
After.
201.
That just be.
That's the length of each string in this array. So that's 201 across and basically 1,000 strings. So it's a two-dimensional array of characters, but we can think of it as a one-dimensional array of strings. Okay? Don't start messing with car star star, car star, bracket bracket, all that kind of stuff. It's going to make your life harder. Okay? If you really, really want to make your life harder, go for it. But you don't have to. The reason you don't have to is because I'm giving you these limits on how big this array is. The reason we have to say char star star when we do argv, because we don't have these predefined limits. We don't know how big each string is. We don't know how many strings we have, right? But I'm deliberately telling you this is the largest that your index is going to be, which means anytime that you deal with the index, you can just hardwire the dimensions like this. Okay, and I guarantee that will save you some energy and time. So don't start using mallocs either, right? There's no need because we know exactly how big this index is. So statically defined arrays. And then how do we know how many times each of these phrases occurred? You're going to want something like a count array, which is just going to be an array of integers. And these are parallel arrays. So if we have a phrase here at index 2, we want to know how many times it occur, well, it's whatever is at index 2 in our count array. Okay. Now if you want to use structures, go for it. That will make your life easier, actually, if you know structures. If you don't know structures, don't worry about it. Use parallel arrays. Okay, one array of phrases, one array of counts. But it works, that's what structures are for, basically, so you can just have one array. So it's up to you. The other thing we're going to need is we need to know how many things we actually have in these arrays, because remember, arrays don't have a sort of native length. So this will hold 1,000 phrases, but how many phrases do we actually have stored? So we can have something like an index length. And maybe we'll initialize that to 0, but that tells us how many things we actually have in these two arrays. So the usual array plus length. All right, you can use code from standard IO, string, ctype, and standard lib. And the string routines will help you. There's string routines for doing comparison, for copying strings, and so on. Feel free to use those. So here's a sample input and output pair. So you can copy and paste this from the assignment into a file. Sample input, and here's what the output would be in that case. All right, so everything uppercase, et cetera, et cetera. All right, still with me? So if you go on to the Linux server, look under /temp. There's a big test file called War and Peace. Just search /temp for it and you'll see it. And it's 63,000 lines of text. And it's a really good test file to run your program on. So I'm going to run PA4 and run it on War and Peace. And I'll put my output into more. And so O occurs 259 times, A occurs 171, Y 77, 18057, and so on. And a lot of these longer phrases only occur once. And some of them, you can see this one got cut off at 200 characters. But if you're doing something slightly wrong with your arrays, there's a good chance it'll blow up when you run it on War and Peace. Okay. One thing you do not want to do is read the input and store it in a big, huge array and then start processing that array. Right? That'll blow it up. Read your input character by character, do what you need to do, store your phrases, keep going. Okay, don't try to pull everything into memory and then process it in memory as one big long file. That's not the best approach. If you do this, you can sort it and you can see like the most common phrases. So yes is the most common phrase in War and Peace, 507 times. My dear fellow is 56. Right, so you can play around with this. All right, suggestions. Obviously, you want to think about modularization. You want to try to break this into pieces that make sense to you. But here's some suggestions for some pieces to work with. A way to read from standard in and pre-process the characters. That's your super duper magnificent get car. A way to detect the beginning and end of phrases, and we'll put together some pseudocode next and see how you might use that. A way to store a phrase into a dictionary, either as a new entry or to bump up the tally of how many times you've seen a phrase. A way to sort your dictionary, obviously, and then a way to print your dictionary. And try to test it with long phrases and also with things that go beyond 1,000 phrases. So War and Peace is good for both of those. Lots of comments in your code, okay, meaningful comments, but you're going to have lots of moving pieces in here. Document them as you go, okay, it will help you. And whatever you do, if you do this as a single .c file or if you break it into separate files, if you put it in a make file, whatever your choice, pull it all into a single tar file, upload that tar file through Canvas. Okay, that's your submission is a .tar. Practice with tar files ahead of time. Don't destroy your hard work the night before. Okay. All right, so what does this look like? What's our main program do? Let's read a phrase from our input. Let's save the phrase in our index. And let's just loop. And we'll do that until we've read all the phrases. And then let's sort the index. And then let's print the index. And we're done. There's your main program. Pretty simple, right? Now, it doesn't do anything, but it's a nice sort of framework on which to build. And this doesn't have to be your main program. Okay, you can come up with your own version of this. But to me, this is a pretty straight rendering of what the assignment is. Read a phrase, save it. Read a phrase, save it. When you're out of phrases, sort your phrases, print them. That's the end. So now I got to write 4 functions. One to read a phrase, one to save a phrase, one to sort my index, one to print my index. And I don't even have to write code for this first, right? I might decide I'm just going to work on my reading a phrase code. And how do we read a phrase? So I'm going to write a function called read a phrase. It's going to take an array of characters that I'm calling phrase, and it's going to return a phrase in there, right? And maybe I'll make this whole function have a return value where 0 means end of file, and 1 means I didn't hit the end of the file, so I actually have a phrase. So now read a phrase not only gives me back a phrase, but it also gives me information about did I hit the end of the file, which means that I can put this into a while read a phrase, save phrase, 2-line while loop, right? And then when read a phrase returns 0, my while statement will fail. I'll kick out of there, do my sort and print. But again, you're welcome to do what you like. But try not to use global variables, because globals can be dangerous. All right, so how do we read a phrase? Well, phrase begins with a non-space character other than punctuation. It's a collection of things other than punctuation, and then it ends when we hit punctuation. So here's an idea. So C equals my super duper fantastic get car. That's your routine. If C is not the start of a phrase, I can go back here and read another character. And if that's not the start of a phrase, I'm going to go back and read another character. So I'm doing this first thing over here where I'm looking for the beginning of a phrase. And this start of phrase basically tells me, is my character something other than a space or one of those 6 punctuations? So it's just a big glorified if statement. So when I get down here, I know that C is the first character of my phrase. So I'm going to save that. And where am I going to save it? Well, I'll have some output index, which I'll initialize to 0. So I'll say phrase bracket out index equals C, and I'll do a post increment. So it automatically goes up by 1. And now our next thing to do is keep reading until we get to the end of a phrase, one of these 6 punctuations. So C equals my super duper fantastic get car. If it's not the end of a phrase, well, I want to save it in my output, so again I'll say phrase bracket out index plus plus equals C, and then I'm going to go back up here, get another character. If it's not the end of the phrase, save that in our output and keep doing this. Otherwise, if we've hit the end of the phrase, all we got to do is null terminate our phrase. So the way I'm doing this, out index is always the next location to write in phrase. So I should be safe just saying phrase bracket out index equals null terminator. And then I'll just return 1. Now you have to do something in here to detect end of file. But that's just kind of some special cases in here. Every time that you try to get a character, check to see if you got the end of the file. And if you did, just return a 0. You're done. Otherwise, we've built up this character array phrase to be what the next phrase was from the input.
You might want to be doing some cursive.
And we return a 1. You could, but be a little careful with it because these phrases can be kind of long. So there's your read a phrase. Now, if you decide this is going to be one of the first functions you write, what can you do? You can code this up. If you don't want to deal with my super duper get car, don't worry about it. Just use get car and understand that lowercase letters will be lowercase, new lines will be new lines, parentheses will be included, and so on. But just don't use those in your test cases, maybe, right? Or don't be tripped up by seeing lowercase letters, right? If your goal is to just nail down this logic of building up a phrase, right? You don't have to follow the assignment's instructions. The only time you have to follow what the assignment says is when you're actually submitting your final code. In the 2 weeks up to then, you can ignore it completely if you want, right? So do what makes sense for the sake of developing pieces of this. And if you don't want to deal with all the weird punctuations, you know, you can say start a phrase is just a letter, end of phrase is just a period. Nothing wrong with that. Right? Now you can't leave it like that for your final if you want full points, but to develop the logic of this, go for it. Or just start with writing start a phrase and end a phrase. And now, type in a bunch of characters and have it print out something when it finds the start of a phrase, when it finds the end of a phrase. And you can test those. And now put this together and type in a bunch of stuff and just have this thing, have a main program that calls read a phrase repeatedly and just prints out the phrases. And now you can stuff in a bunch of text and it should just print out what you think of as phrases. So all kinds of ways you can develop this and you can test it, right? And the goal is once you've got this working, you don't have to think about it, right? So now I'm trying to tally up my phrases. I don't want to be thinking, wait a minute, what do I do with a parenthesis, right? What do I do if there's spaces inside this phrase or if there's spaces after the period, right? That's all taken care of in here, right? And now I don't have to think about that. It's not distracting me. Now my goal is I just want to write this thing that saves a phrase in the index. And I have confidence that the phrase that I got back from this step is a phrase, right? Whatever that means. So how do we save a phrase? So we've got a save phrase routine. We pass it a character array, which is a phrase. Well, let's say we called get phrase and we got the phrase hello. And this is what our memory looks like right now. Okay, we've got an index array, we've got a count array, we've got index length equal to 0. This tells me there's nothing in my index. It tells me the next phrase I store should go at location 0. So if I've got the phrase hello and I just called save phrase hello, I look at index length that's 0. This is where I store hello. And since it's a new phrase, I've seen it exactly once. So I set the corresponding element in my count array to be 1, and I increment index length. Okay, sanity check. What does index length mean? It means I have 1 phrases in my index. Sure enough, there's index. There's hello. Okay, now I get the phrase, this is fun. Well, I've got to see if this is a phrase I already have. So I want to look at every phrase that's in my index. And this tells me how many phrases I have. So I'm going to do some kind of loop to look at all my phrases until I've checked one of them, right? So I'll check this one, and that's not the same as this is fun. So I'm going to go to index length, and I'm going to store my new phrase there. This is fun. And I'm going to set the corresponding count to be equal to 1. And I'm going to increment this to 2. Now I got 2 phrases. Now I see this is fun again. So I compare this is fun to this, and it's different. I compare this as fun to the next entry, and it's the same. So instead of storing it somewhere and changing index length, I just increment the corresponding count. So what's this algorithm look like? So we'll go from 0 to index length. And if that element in our index matches phrase, then this phrase is already in here. All we want to do is bump up the corresponding count. So we can increment count bracket I and return. We're done. If entry I does not match phrase, go back to the top of your loop and try the next entry. So this will iterate through all of your phrases in your index. If it finds one that matches your input phrase, it bumps up the count and it exits. What happens if we get all the way through this for loop and we come down here? What does that mean? Yeah. So if we're down here, we've got a new phrase. All right, well, if we've got a new phrase, so index len tells me how many phrases I have. If this was how memory looked and I got a new phrase, what index would I store it at? 0, 1, 2, 3, or 4? 2, right? And index len is 2. So my theory is index len tells me where I should store my new phrase and where I should store the corresponding count. And that's how arrays work when you start from 0, if you do this kind of length, right? If this is the number of things in your array, it's also the location where the new thing would get stored. So it's a new phrase, I could say copy phrase to index bracket index len, and then set the count equal to 1, and then bump up index len and return. And that's basically your save phrase routine. Now there's one detail, which is we're only going to store 1,000 phrases, and if my index len gets to 1,000, this is going to blow up, because I'm going to try to access element 1001, right, index 1000. So in here I would just say if index len equals 1,000, I'm just going to return. I'm just not going to store the phrase, I'm not going to set a count, but no one's going to know that. My caller doesn't know that. It called save a phrase, and the fact that I didn't actually save a phrase doesn't matter to the caller. And the same thing over here when we're reading a phrase, right? If your phrase is longer than 200 and phrase can only hold 200 characters, this will potentially blow up. So somewhere inside here where you're doing this, if your index gets to be 200, you need to null terminate your phrase and return right away. But you also want to read the rest of the phrase first, so don't return right away. Set a flag and just stop saving. So details, right? But again, if every time you read a phrase you're using this piece of code, this is the only place you have to worry about that detail. If every time that you're saving a phrase in your index you're using this piece of code, this is the only place you need to worry about that detail. So you know how to read a phrase, save a phrase. We'll talk Monday about sorting. We can just use a bubble sort, right? And printing is just a for loop. Just go through, print each element from your index and each count. Okay, so if you start coding this, right, seeing if something matches a phrase, you want to use string compare. Don't use double equal, because double equal doesn't tell you if two strings are the same. Okay, use string compare, look at the man page for it. And if you want to copy a phrase from one place to another, use string copy. Don't use equals, because equals just copies pointers. String copy actually copies character by character from one chunk of memory to another. So those are all in string.h, and they have man pages. String comp compares two strings to see if they're the same. So instead of saying is index I equal to phrase, see if string comp index I comma phrase is equal to 0. If two strings are equal, string compare returns 0. All right, that's a start on PA4. So we'll talk about sorting on Monday, but think about this, kick it around, write some code, bring some questions Monday, and we'll go into details. All right, see you next time.